This part of the video lessons is talking about the velocity selectors. What a velocity selector is a device that is used to select charges that are moving with a certain velocity. So velocity selector is the word is saying it. Now, this consists into a uniform electric field and a constant magnetic field that are perpendicular to each other. So when we see that a charge is entering between two parallel plates, we know that it's experiencing an electric field, electric force. And as it is entering into the magnetic field, it is experiencing a magnetic force. Now, electric field and magnetic field both are perpendicular, so is the velocity of the charged particle is perpendicular with those two fields. And then on this way, it is selecting, what the velocity selector is selecting charges that are moving undeflected into this equipment. I will bring a picture here so that we can have it a bit more clear. So what we have here is two parallel plates that are creating a uniform electric field, E. In this particular case, the positive charged plate is on the top part and the negative charged plate is on the bottom. So the electric field between those two parallel plates, it's always leaving the positive going toward the negative. Okay, and what we have here is a magnetic field, a uniform magnetic field that is into the page. Okay, so into the page. Now, as a positive charge is entering, so when we have two parallel plates, positive plate is on the top and negative plate is on the bottom. Then we have a positive charge that is entering here. The electric force that the charge will experience will be going down. Okay. And now, on the other hand, since the electric field and the magnetic field are merged together, what we have on the situation of that, the magnetic field is into the page, and you have a positive charge that is entering into this field. Then let's see, based on the third left-hand rule, what is the force that the charge is experiencing. So since it is positive and we are using the left hand, we will switch the direction. So instead of going east, we will go west. Magnetic field is into the page, so your fingers should be into the page. Therefore, the magnetic force is going up. And this is why what we have on this picture is the electric force is going down because of what we said, and magnetic force is going up because of the third left-hand rule. Now, what we are looking for is to select charges that have a certain velocity, okay? Certain velocity. To go through, to enter through this hole and then go undeflected on the other side, the other hole of the tube, okay? So, the word undeflected means that the force net is equal to 0. So force net is equal to 0. Now again, since the gravitational force is way smaller than both of them, the magnetic force and the electric force, then we can say that the only forces that the object is experiencing is magnetic force and electric force. Okay, so if they are if the charge is moving undeflected, that means that those two are equal to each other in magnitude, but opposite direction. Okay. Now, since we have a charge that is between two parallel plates, so the electric force is Q times magnitude of the electric field, E. And since we have a charge that is moving into a magnetic field, then magnetic force will be QVB. So Q is canceled out, and then from here, V will be equals to E over B. And this is the relationship that we have to use to identify what is the velocity, the speed when we have an electric field strength and a magnetic field strength. Okay, so now as an electron is entering into an electric field that is with 5.20 times 10 to the power 5 newtons per coulomb, and a perpendicular field of, let's say, 3.80 times 10 to the power of -2 Tesla, and it is passing through both fields undeflected. So those two fields are combined. It's not that they are one after the other, but they are merged together. Then passing through undeflected. What is the speed of the electron? What is the speed that the electron is having as it is between those two? Okay, so now undeflected means that the electric field is equal to a magnetic field, considering that the object is having a mass, or therefore a force of gravity that is way, way smaller than electric force or magnetic force. So force net will be just the electric force and magnetic force, not B. Okay, so the free body diagram on that case was that the electric force was going down and magnetic force was going up. But they are always either one is up and one is down so that they can cancel out. Okay? So if the electric force is this way, magnetic force should be this way in order to cancel out. Or if the magnetic force is this way, then electric force should be this way so that they cancel out. There are questions so that they may ask you what is the direction of the magnetic field when you know only what is the electric force. Okay, and then based on the fact that you can draw the conclusion on which direction is magnetic force, then you can figure out what is the direction of the magnetic field. Okay, we'll see those kind of questions in class, so please do not miss that, those classes. Okay, so now since those two are equal to each other, then electric force equal to magnetic force, and since we have an object or a charge that is entering into two parallel plates, so then electric force is E times Q, and since we have charge that is moving into a magnetic field, that magnetic force is Q charge moving into a magnetic field. So charge and charge is cancelled out, is irrelevant. And then we have the velocity as E over B. or in our case, will be 5.20 times 10 to the power of, what was it? 5, okay, 10 to the power of 5 over 3.80 times 10 to the power of negative 2. And when you enter this in your calculator, you will have 10 to the power of 5 divided by 3.8 times 10 to the power of negative 2. It is 1.37 times 10 to the power of 7 meters per second. So this is the velocity of the electron. Okay. Let's see now another example. So let's suppose that we have an ion now that is moving with traveling with a speed of 3.50 times 10 to the power of 7 meters per second, and it is traveling through a velocity selector. Then the magnetic field strength that the velocity selector has is 0.500 Tesla. What is the electric field that the velocity selector has? So what is E? Now, again, let's deal even with some directions here. So let's say that it is entering east, and then magnetic field is going out of the page. And let's see now what is the direction of the electric field and all that stuff. Okay, so now we have ion that is +2. Okay, and then we have two parallel plates, which we don't know. We will define the nature of the plates as well here, and we will define the electric field as a vector as well. Okay, so we have two parallel plates, and then we have a magnetic field that is out of the page, merged into this. It's a uniform one. So what do you see here is that, well, that here is not quite evident. It is a uniform one, magnetic field 0.500 Tesla is out of the page. And then we have a positive ion, we know it's +2, that is entering east. Okay, a positive, whatever is about. Now let's see, based on this, what do you think that the magnetic force is going to be? Since we are using the left-hand rule, then we have to switch the direction of the thumb from east to go west. Magnetic field strength is out of the page, so your fingers should be out of the page. Therefore, the magnetic force is going down. In order for the ion to be undeflected, we should have an electric force that is going up. Okay. Now, since the electric force is going up and we have a positive charge, then that means that this is the negative plate and this is the positive plate. This is how you define the polarity of the plates. Okay, so again, let's do it again. We know that we have a positive charge, and since we are using the left-hand rule, we will switch the direction of the charge. From the east, we will go in the west direction. The magnetic field strength is out of the page, so your fingers will be out of the page. Therefore, your palm, which is going down, will be the magnetic force. Now, we define the magnetic force. Since the object is moving undeflected, that means that the electric force is going up in the opposite direction of the magnetic force. So this is why we drew the electric force up. Now, the electric force up and the positive charge that we had entering between the two plates dictates that the upper plate is negatively charged, therefore the lower plate is positively charged. Good. Now let's work with the values. So now what we have is electric force is equal to magnetic force, or QE is equal to QVB. So electric force is equal to V times B, or 3.50 times 10 to the power of 7 times 0.500. And then the electric force will be, electric field will be 1.75 times 10 to the power of 7 newtons per coulombs. Let's take a look now to a more complicated problem. So we know now what the velocity selector is. Now, a velocity selector has a magnetic field strength of 4.0 times 10 to the power of -2 Tesla, and a uniform magnetic field that is perpendicular to a magnetic field. If the electric field is produced by two parallel plates that are apart, delta D, 1.50 centimeters, which is 1.50 times 10 to the power of -2 meters. What is the potential difference between those two plates so that a charged ion will, with a speed of 4.20 times 10 to the power of 6 meters per second, will pass undeflected through the selector? Okay, so we have a magnetic field, and then we have an electric field that is produced as the presence of the two parallel plates that are apart 1.50 times 10 to the power of -2 meters, and the charge is moving with 4.20 times 10 to the power of 6. Okay, so when we have two parallel plates, the electric field strength is a uniform one, and we have dealt with it. It's the same on every single point between the two parallel plates. And it is delta V over delta D. So in order to find the delta V over delta D, in order to find delta V, what we have to know is what is E, because delta V is equal to E times delta D. So then this gives us the clue that we will use the fact that the ion is moving undeflected and force of gravity is ignored. So QE is equal to QVB. So E is equal to VB, or 4.20 times 10 to the power of 6 times 4.0 times 10 to the power of -2. Enter this in your calculator, and we will have an electric field strength of 4.2 newtons per coulombs. Now, on the other hand, as I said, E is delta V over delta D. So delta V will be E times D, delta D, or 4200 newtons per coulombs times 1.50 times 10 to the power of -2 meters. So times 1.50 times 10 to the power of -2, and delta V will be 630 volts. I think, yeah, 630 volts. Okay. Okay, this concludes the velocity selector part of the lesson, and we will deal with any questions or any problem or concern that you may have in class. I hope that you understood what we were doing.